Ladies and gentlemen, welcome back to another episode of Double Award Physics. We are on Waves 2.1.2 from the CCEA course, and this one is all about frequency, wavelength and amplitude of a wave. So I've got myself a rather dodgy looking wave here, and we're going to take a look at its anatomy. It is a short episode, should be reasonably quick. Okay, so things to know about waves. When you experience a wave in a test situation, usually you get it as some form of graph. And the key thing here is usually up the side you have some form of displacement or distance, or something measured in meters or centimeters or a distance. Okay, up the side. Across the bottom you can have one of two things. You can either have distance again, or displacement, if we're in vectors, or time. Okay, and that will usually be measured in seconds. Now, of ultimate importance when you're in exam, look at this. Okay, first thing you do when you see a wave, look at what's across the bottom. Okay, because that will inform what you can actually get out of this graph. Okay, so let's have a little look. Let's assume that we have a distance graph. Okay, or displacement. Okay, distance and distance in meters. Okay, so what we're saying is basically this is in the upward direction, in the up and down direction. This is the kind of movement of an individual particle, and across the ways it's the progression of the wave. Alright, now the information that we can get from this. Alright, the distance between two crests, two troughs, or any two identical points on subsequent waves, this is known as the wavelength. Okay, it's measured in meters because it is a length like everything else. Okay, easiest way to get it are crest to crest and trough to trough. The reason the other ways are difficult is because we said that it was two identical points. Okay, so this point here, the immediate kind of thought is that this point here would be its immediate kind of counterpoint. But the problem is that this wave, from a simple look at it perspective, this wave is going down, and at this point it's going up. Right, so they're not completely identical. Okay, their vectors are slightly different, which makes them sufficiently different for them not to be points apart. Okay, so this bit here is actually over here because the wave goes up, down, all the way up again, and at this point again it is heading downwards. Okay, so they have the same distance from their original position. They are going in the same direction, so these are identical points, this one and this one. Okay, so that's the wavelength, and that's assuming that we have distance across the bottom. Right. The amplitude of the wave, okay, is its maximum displacement from the zero position. Okay, so essentially that's how far up it is between a crest and the x-axis, or trough and the x-axis. Okay, so either of those, that is your amplitude. Alright, now you get the sneaky examiner syndrome here, okay, where they may give you this situation. They just give you the graph like this, copy the axis as well, why not? Okay, but instead of having the x-axis there, they have it down here. Okay, for no great reason. Okay, they have, this could be a picture, or it's they're saying this is a diagram of a string rather than a graph. Okay, now in this case, if you're being asked what the amplitude is, you measure the full height of the wave and then divide it by 2. Okay, so amplitude equals full height of wave, and super importantly, a big line divided by 2. Okay, so full height of wave divided by 2 is your amplitude. Now, after that, good stuff. Okay, so that's it if it's a distance graph. Right, now, the issue arises when it becomes a distance time graph. Okay, so instead of this remains the amplitude, that's quite good because this axis hasn't changed. So anything going on the y-axis isn't affected, but this is no longer the wavelength. Okay, the distance between two crests and two identical points does still have a meaning, okay, but it has the meaning of, it is the period of the wave. And when all the boys have stopped giggling, okay, the period of a wave is how long it takes for a complete cycle. And that means the same thing in girls as well. Okay, it's one full cycle of a wave. So between crest and crest. And the period is measured in seconds. It's a time. Okay, how long it takes for a single wave. Alright, now sometimes in equations we would quote the period as being t, the capital T. Okay, as opposed to time, which is a little t, period is capital T. Alright, now that doesn't help us with what 2.1.2 said, which says explain the meaning of frequency. But in order to get frequency, you have to understand period. Period is the amount of time it takes for a single wave to happen. The frequency, okay, of anything, is how often something happens in a particular period of time. For a wave, it's how many waves occur or pass a point in 1 second. Okay, and mathematically, that is written as frequency, or frequency, frequency, equals number of waves divided by time. Okay, so if I have 10 waves in 20 seconds, it would be 10 divided by 20, which would give me a frequency of 0.5. If I have 50 waves in 50 seconds, it would be 50 divided by 50, giving me 1. Okay, the unit for frequency is the hertz. Okay, GRTZ, and that's abbreviated to HZ when you're using equations. Okay, so it's 1 hertz, 2 hertz, 3 hertz, 4 hertz. It's one of those annoying things. It doesn't have a singular. Okay, so it's not 1 hertz. Okay, but frequency is also found by the period as well, because if the number of waves is 1, then the time is the period. Does that make sense? Because the period is only how long it takes for one wave. If the number of waves was specific, if it was made as 1, then it would be 1 over the time for one wave, which is the period. Okay, so frequency is 1 over the period, or F equals 1 over T. Okay, and that leads us to a couple of little mathematical triangles. If you're big on learning stuff, that frequency equals the number of waves, which we'll call n, divided by the time little t. Okay, so if two things are sat beside each other, remember they're multiplied, and if they're above and below each other, they're divided. Okay, but also, duplicate that, frequency equals, in the very special case, 1 over big T. And now this 1 over big T, it's not anything special, it's just if n was 1, then little t becomes big T. Right, marvelous. Right, so that's frequency sorted out. Wavelength, it's the distance between a crest and a crest on two subsequent waves, or a trough and a trough. The amplitude is how far it gets away from its original rest position, and then all we're left with is we need to have the relationship between frequency, wavelength, and wave speed. Okay, so at this point it's probably quite useful to introduce the concept that wavelength gets an annoying Greek symbol, which is super irritating to do when you're typing. Okay, but if you use symbol and L, okay, wavelength is lambda. Okay, it's an annoying Greek symbol. That's it there, and I don't know why we don't just use W, but there it is. Okay, so wavelength is lambda in any form of equation, and the general rule of thumb is that the wave speed equals the wavelength multiplied by the frequency. More often written as V for velocity more than speed equals the frequency F times lambda. Okay, so V equals F lambda. And that brings us to our final little triangle for today. That the wave speed V equals the frequency times the wavelength. V equals F lambda. Okay. And then let's just recap with a nice simple example. Let's assume that we have 40 waves are produced in 10 seconds. What is the frequency? Need to get a quieter keyboard. Okay, so what is the frequency? So we start off with our little equation from back here, f equals n over t. Okay, so what is the frequency? Grab that. So f equals n over t. Remember, formula working answer unit at all times. So f equals 40 waves in 10 seconds. So f equals 4 hertz. Alright, good stuff. Now, let's see if we can get a distance graph in here. So grab these so we can give you a proper form of question. So let's assume the question says, right, you've got 4 hertz and here's your distance graph. Okay, so distance on the y-axis. We'll have to change that to distance on the x-axis. And it says that this length here, all the way across, says this length here is 8 meters. Okay, so it's the same way, 4 hertz, this big distance here is 8 meters, and I want you to find the velocity. Because the first thing you realize is that they haven't given you a single wavelength, they've given you 2. Because a single wavelength is from here to here, just half that distance. So, because you're nice, intelligent people, you're going to write down the side of the page that lambda, okay, so we go to our symbol again, lambda, and it's going to equal 4 meters. Okay, f equals 4 hertz, and v is unknown. So our equation is, quick copy of that so I don't have to go through that rigmarole again, v equals f, not down a bit, v equals f lambda. So v, that would seem that I do have to go through that rigmarole anyway. So v equals f, which is 4, times lambda, which is also 4. So v is equal to 16, and because my lambda was in meters and my frequency was in hertz, then it's a nice standard meters per second for my velocity. Nothing to it. Nothing to it. Okay, so see you next time for 2.1.3.